After watching this video, you should be able to understand what a closed system is and to make calculations involving thermal energy transfers and temperature changes in closed systems. Thermodynamics is the branch of science or physics or engineering that deals with thermal energy transfers and work done by thermal energy transfers. A system is the name given to any body under study, and in fact a closed system is one which is defined by boundary walls that enable the exchange of energy to and from the body. The system can also have work transferred to it by other means instead of thermal energy. So a closed system can have thermal energy either transferred to it or transfer thermal energy to the surroundings itself. But it can also have mechanical work or other types of work, electrical perhaps, of energy transferred to the system or done by the system. The first law of thermodynamics states that during any interaction or energy exchange between a system and its surroundings, the amount of energy gained, whether thermal or otherwise, by the system must be exactly equal to the amount of energy lost by the surroundings. So, for example, if the system lost 5 joules of energy, then the surroundings must have gained 5 joules of energy. Or if the system gained 5 joules of energy, then that must have been lost by the surroundings. Now, in this video, we shall only be concerned with thermal energy transfers. So the equation is the thermal energy transfer depends upon the mass of the system, specific heat capacity of the system, and the final and initial temperatures of the system. Let us consider the following closed, isolated system. Isolated means that it cannot exchange energy with the surroundings, only inside it. Let's introduce another body into this closed system. So what is going to happen here? Looking at the temperature differences, 50 degrees C and 10 degrees C, obviously the water will transfer thermal energy to the aluminium, Al. Let us also consider adding to the system 0.2 kilograms of iron at a much higher temperature, 200 degrees C. In this case, the iron being at a higher temperature than the surroundings, which is water, will lose thermal energy to the water. So what will happen eventually? The whole thing will stop exchanging thermal energies when it has reached an equilibrium temperature. Now, since we don't know what the equilibrium temperature is, let's just call it T equilibrium, TE. We see in this case that the aluminium goes from 10 degrees to the equilibrium temperature, the iron goes from 200 degrees to the equilibrium temperature, and the water will go from 50 degrees to the equilibrium temperature. So there are thermal energy exchanges that are happening to reach the equilibrium temperature. These thermal energy exchanges can be calculated by using the formula Q equals mc delta T. Considering the aluminium, we can apply the equation Q equals mc delta T as follows. Q is the thermal energy exchanged by the aluminium, m is the mass of the aluminium, C is the specific heat capacity of the aluminium, T final is the equilibrium temperature that the aluminium will eventually reach, having started at a T initial of 10 degrees C. So let's put in the numbers. So the mass of the aluminium is 0.1 kilograms. The specific heat capacity of the aluminium is given. It's 910 joules per kilogram Kelvin or Celsius. And the final temperature is the equilibrium temperature, which is unknown, so we will leave it as TE. The beginning temperature of the aluminium was 10 degrees C, so we will put 10 degrees. We can repeat this for the other two materials, or in fact parts of the system. Repeating the calculations for the iron and the water, we have the following two equations. The important thing to remember that as a closed isolated system, no thermal energy can escape or enter, and therefore the total thermal energy in here could not have changed. So when we add up the changes happening to the aluminium, the water, and the iron within the system, we should get a total of 0 change. There's been some internal changes within the closed system from the iron to the water and from the water to the aluminium, and the total thermal energy has remained unchanged. So when we add up these values for each individual one for the thermal energy transfers, we should get 0. So we end up with this mathematical equation whereby we add up all the thermal energy transfers that are happening within the closed system, which should equal 0. And the only unknown that we have is the final equilibrium temperature. Therefore, one equation with one unknown, if we take care through the calculations, we should be able to find the equilibrium temperature. I challenge you to do so. The first person with a correct value shall be awarded extra credit. Begin and good luck.